Okay. What is 3 to the 1? 3. Okay, so that should be 3. What is 3 squared? 9. 3 cubed. 3 to the 0. 1. What is 3 to the negative 1? 1/3. Love it. What is 3 to the negative 2? 1/9. Then the next one would be? Great. Okay. So this is what we call, just in terms of what I call this function, it's called an exponential. So because there's an x in the exponent, it's called an exponential. Notice how, like x squared, for instance, this is not an exponential. This is a quadratic because the variable is in the base. So if the variable is in the base, it's a kind of polynomial. If the variable is in the exponent, it's an exponential. All right? So these two are inverse functions. The property of inverse functions is you switch the x and the y. So if I'm making a table of log, I take its inverse, it's just the inverse of this. So the x values would be -127, and the f of x value would be -3. So log base 3 of x is the inverse of 3 to the x. What does the word inverse mean? It means the x and y are switched. So like if you were to make a table of x squared, and then make a table of the square root of x, those are inverses, right? X squared and square root of x. It would be the same, but like the x's would be in the y spot and the y's would be in the x spot. And that's what logs are. So that's how I want you to think of logs right now, just the inverse of exponentials. The same as an exponential, but the x's and y's are switched. Not too bad. You just switch the x's and the y's. Switch the x's and the y's. That's it. Okay, so let's look at what these graphs look like. You ready to graph them? Okay, 3 to the x. 0, 1 is a point. Boink. 1, 3. 2, 9. Before I graph the rest of the points, I'm going to actually graph these both at the same time because I really want to like hammer in the relationships between them. So 0, 1 becomes 1, 0 for log. 1, 3 becomes 3, 1. 2, 9 becomes 9, 2. Now let's do the negative in fractions. So -1, 1/3. 1/3, -1. -2, 1/9. So I'm very close to the x-axis, basically. Just make it a hair above the x-axis. -3, 1/27. It's practically on the x-axis. And then it'd be 1/81st, 1/243rd, 1/729th, etc.
Does it ever reach the x-axis?
It never reaches the x-axis. So there's an asymptote there. Okay, so this is there's an asymptote at y equals 0. All right, you ready to do so we got on the log base 3 of x. And that's how you would say this, by the way, log base 3 of x. Log base 3 of x. Okay, okay, so we did 1/3 -1. Now we do 1/9 -2. So very close to the y-axis, just a hair away. And then I got 1/27th -3. So basically on the y-axis there. Yes, because the x and the y are switched. So y equals 0 becomes x equals 0 for the inverse, right? I'm taping this right now, so FYI, this is being taped. I'm gonna post it to my, yeah, serious, yeah. My phone's right there. Yeah, so certain ones I'm going to encourage to learn it. I'm gonna post a video and give them materials and things. We'll see the actual yeah, I have 2 students in mind, but I would like 5 of them too, but
Everybody wants me that.
You better cut that out of your video. Uh-oh. Yeah, probably. No, only the ones there's in there.
Oh,
They're not all gonna watch.
so you just are gonna hear it.
Yeah.
So you're gonna be on YouTube.
Yep. Yeah, this is going on this video. These Wednesday classes I'm filming, and I'm gonna put it on YouTube for the seniors to watch.
It's not like illegal. You're filming this
Oh, because she told us.
Yeah.
She's only filming herself.
No, I'm only filming the board and like my hand.
Well, our video, our voices are in it, so that's.
So how do we know this isn't like a voice fraud?
We did.
Okay, so exponentials grow very quickly. This typical exponential, of course, there's transformations and ways to vary this, but exponentials increase. Yeah, we with this increases the whole time and very rapidly, very rapid, more rapid than like x squared, x cubed, x to the fourth. Very rapid growth. Okay, logs also increase, right? Yes, logs also increase. So even though they're inverses, they both increase. Logs increase very slowly. Okay? You go up very slowly, right? So as fast as exponentials grow, logs grow just as slowly. Okay, take this, put it aside. Let's take notes.
Are there negative exponentials?
Yeah, definitely. Like exponential decay, have you ever heard of that?
Probably.
Probably. Like when things decrease.
So it would be decreasing
Yeah.
faster and slower.
What?
Said it would be faster and slower.
We're doing all this today.
No, clearly not. What?
Decreasing fast and slow?
It'll still decrease really fast. It would decrease really fast. Here, look at there. I have posters actually decreasing. If you turn around on the right side is decreasing. Okay, yeah. So I decided for Wednesdays to just keep as much of it in as few packets as possible, so that way I'm not giving people like 4 different things, and we just have fewer to keep track things to keep track of. So our classwork is in here. So this is not just notes. This is also classwork. And it will last us well more than a day, and I'm sure we'll get to all of it. All of us. But maybe some of us will get to all of it, because people work at different paces. So, let's see here. Let's just like slip down. I should get a tripod. It'd be convenient. Okay, you guys got the date down? 26th?
Today's the 26th.
Yep. Yikes, right? Okay. Properties of ln of x. So what is ln even a thing? So actually, I wanted to start on this slide. I wanted that slide to be on the front, because it's a good reference, so I wanted it to be on the front, but I want to start here. So the definition of natural log, okay? There are different definitions, but this is the one I like to use. The definition of natural log, okay, definition of y equals ln of x. Have you seen ln before?
Yes.
Natural?
We talked about it a lot last year.
Last
year,
I didn't
Nobody
understand
got
any of
any
it.
information.
Really?
It was just last year math was the worst. Mr. Rudy was such a good teacher, but it wasn't hard.
It wasn't
Oh,
very
you're
good.
saying
this on camera.
Okay, yeah.
Show Mr. Rudy. It's just that we all just ignore it.
I couldn't understand the
Yeah.
virtual screen. It just wasn't helping.
It just wasn't helping? Okay, so definition of natural log is the area.
Is that an L or?
It's an ln,
Is it a small x or a big x?
small x. Just like a regular old x.
No, I mean like a small x is in like a subscript x.
Oh, no. Nope. Okay. No yeah. Okay, the area between, okay, the function y equals 1 over x and the x-axis starting at 1. At x equals 1. I like this definition. Most teachers don't teach it this way, but I like it. Because it's visual and is like helps us understand it that way.
Some teachers teach this like in pre-calc.
Yeah, they all do. This is like
So I
standard.
was gonna say, this also is looking for my own.
Yes, yes. You should have definitely learned
I
this.
think I have a whole, I don't remember anything from last year.
Great. This is why I'm put these slides in that this is like a pre-calc thing. But even like when I taught my kids pre-calc at my old school, I still reviewed it because like people forget. Okay, so this is 1 over x. Do we recognize this as a rational function? This is what 1 over x looks like. Okay, this is y equals 1 over x. It's called a rational function. Rational is just a word that means fraction. So if you have x in the denominator, it creates a fraction. That's a fraction. Rational.
How are like regular numbers, rational numbers?
They are. You can just always put them over 1. You can. So a rational number would be a number that's able to be expressed as a fraction. Not that like it is a fraction, but able to be expressed. Okay. So I'm going to zoom in on the first quadrant, right? So I say between 1 and the x-axis here, right? So this area. See that area there? I'm not going to totally shade it in, but you know.
Oh,
That area is what the definition is talking about. And then it would continue, right? Like it would just keep going, you know.
Does it ever keep going there?
Nope. No, it's end behavior is, yeah, it's
Why
approaches.
did we start at 1?
Because that's part of the definition. Well, it actually has infinite area because it keeps on going up and up and up, so you don't want to you start at 1.
Well, it is still technically infinite because it keeps going.
So like ln of, yes, but you would say like ln of 10,000, ln of something, you would like stop it somewhere. Okay, so what is the area of one of these large boxes? 1. Okay, so all of this has an area of 1. What's the area of one of these tiny boxes? 1/100th or 0.01. Okay, 1/100th. So, yeah. So if you wanted to find ln of 2, for instance, right? What do you think? What part of that is like full? You think it's like 3/4 maybe of a full box whose area is 1?
1 to 2.
Yeah, like from 1 to 2. What do you think the area between the curve and the x-axis is? Like how many hundredths of what percentage of that like whole square, which is an area of 1, is it?
Like
70. Yeah, like 2/3 we think. Okay. So let's see. Does anybody have a graphing calculator in their minds? Can I use? I'll just do it on my computer. Okay, so I'm just gonna enter ln. So, okay, ln of 2. Okay, so we said it was somewhere around 2/3. So let's do ln of 2.69. Right? So that's what the area is. Does that look like it's about the area? Didn't it look like, that's what we said, right? Around 2/3?
Yeah, that would be 66.
Yeah. So we're off by around.
Around.
So you are not a perfect, I'm sorry, you are not a perfect estimator, Jackie, I'm sorry to say. Okay.
Everybody's up.
Okay. What do you think? Let's go to 2.7. Okay. Let's do ln of 2.7. So all of this area, I'm going to shape this one. If I take all of this area, how much would how much?
Adding.
Yeah. So it's just going to get, it just keeps adding. I always start at 1. So ln of 2.7 is that shaded area.
But what do we say it's equal to?
Yeah. So like how many?
1/2.
So maybe I added a half. Wait. So it's like this area, which is 0.7, right? Plus this area.
Out of the box, out of the whole one.
Yeah, so like, you think it's about 1?
But look at.
I agree with Logan. I think, so picture this area, right? and smush
Yeah, that's what I
it
was
here.
just gonna say.
Can you visualize it? Like you could pour this water here and make a full square?
It's like more than
So
It's
like
like
you're
more
not
than
going off to like any
Yeah.
numbers in the graph, you have to like look at the area yourself.
Yeah. I mean, yeah, if you're estimating it, really. Okay, so so Login says around 1, Mariam agrees, you think more than 1, definitely like over 1 by now. Okay, so let's see. Let's
It's
do,
not gonna be one exact, it's gonna be like one.
let's do 2.7.
I knew it was less. No.
No, you
Okay.
guys were over. I literally said less.
Now, 2.71218. We're getting closer, right, to 1?
Yeah.
Yeah? Anybody recognize what this number is? Oh. Nope.
Not
Did
high.
you say?
The other one. E, yes. Ding, 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 ding. Okay. But so the area to 2.7 is about 1. So just FYI, it is about 1. So if you go to 2.71218, 2.72 is rounded, okay? The area, okay, from 1 to 2.72. No, I'll say 2.718. Because then you can tell E. We'll see that in a second. Which is parentheses E equals 1. And that's why E is special.
Wait, 7 and 8.
Is
7,
that
1, 8.
why E is defined as, is that why E is E as opposed to just like any other number?
Yeah, because it's the place where if you take ln of E, you get 1. It's just the input. It's just the number that you input to ln to get an output of 1. And we can see why is the output 1? Because this area is 1. It would be a full box.
What about ln of 3? Is that over 1?
It would be over 1. It would be like this much over 1. How many tenths of a, I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 more boxes. So like another, so 10 100ths.
So there's like no exact one.
Yeah, it's all going to be decimals. Yeah, it's all going to be decimals.
But too many.
But if I put in E here, that's wrong. Yeah, it's very satisfying, right?
Because isn't the natural log like base E?
Yes. Okay? Yes. Okay, so that's how natural log is defined, and that's now we know how E is defined. It's the place where if you stop finding the area there, you get an area of 1. Okay? And also, by the way, I think this is a little bit crazy. Who would have thought there would be such a tight relationship between a logarithm and a rational? Right? Like, this is a really tight relationship between 1 over x and ln of x. Now, like, square root of x and x squared, we expect those to be related, right? Sine and cosine, we expect those to be related. Like, when the derivative of sine was cosine, we're like, okay, fine. Like, that makes sense, you know? But, yeah, we're going to learn that the derivative of ln of x is 1 over x. Yeah. Yeah, so ln of x and 1 over x are tightly related in calculus. Okay, so let's go to front. Let's learn just like properties of ln of x. Now we're going to do algebraic stuff, not really conceptual. We're just going to like get some rules down and stuff and things. This is a graph of it, so notice the key point 1, 0. Yes?
Yes.
So this means, this key point means that ln of 1 is 0. Also, if I'm taking the area underneath 1 over x, right, and I start at 1, because that's the definition, and I end at 1, how much area is that? So let's say I'm taking the area underneath 1 over x, and I start at 1, because that's part of the definition, and I end at 1. How much area? There's nothing there, right? 0. There would be 0 area, right? So ln of 1 is 0. And then here, E, which is 2.718, which is about here. Do you see how this is at E? So ln of E, and this is at 1, ln of E equals 1. So we can see that on the graph. That ln of E is...
Could be any number.
What?
I think E like any number.
Nope. No, E is a very, just like pi. No, it's good. Do not berate him for asking a clarifying question. Safe space. No, just like pi is always 3.14,
Yeah.
15926. E is always 2.718.
Did someone discover?
Yeah, I don't know. Probably Leibniz or.
Obviously, imagine naming
Maybe
yourself. Imagine naming a variable after yourself. Like,
I discovered a variable. I named it JL.
Yeah. Okay, let's get this, not really that important. The function is continuous, yeah? One-to-one, that's like a term we don't really need to know, but that means it's a function and its inverse is also a function. It's actually pretty rare. Normally when you take inverses, the inverse wouldn't end up being a function, but we can pass it both the vertical and the horizontal. Okay, it's increasing. Concavity, we haven't learned that yet, but it's the, so like this is, for you guys, this is decreasing, right? But this is decreasing and this is also decreasing, right? So it has nothing to do with increasing and decreasing. But if it's kind of the curvature, if it's curved like this, like part of a frown, this is concave down. If it's curved like part of a smile, like this would be smiles, it's concave up.
Concave frown.
Yeah, so is this more like a frown or a smile? Frown. So concave down, okay, the whole time. It's positive. Where is this function positive?
Above the x-axis.
Yep, that's what positive means, yes. Where is it? Where is that happening? From 1 onward. Yeah. So from 1 to infinity. Or you could say x, oh wait, I should use parentheses. Or for x is greater than 1, okay? And it is negative, so if you think of like finding the area backwards, like if you're going left, so that'd be like negative area. It's negative from 0 until 1.
Wait, where's that?
Right here. So all of this, just like this little like area here.
Oh, because I was just looking at the zero, like, oh, I have no idea.
Yeah, got it. But it's increasing the whole time. Most functions kind of go up and down, right? You have like different curvatures along the way. This is increasing just like legit the whole time. So what would its derivative be? What sign would its derivative have? So if this is an increasing function, its derivative is going to be positive everywhere. Right? If this increases everywhere, its derivative is positive everywhere. Notice that its domain, you cannot input negatives. You're like not, you know how you're like not allowed to input negatives to square roots? Same for logs.
You can't put 0 in either, right?
You cannot put 0 in either. So it's not, doesn't exist over here. It's not part of the domain. Okay, flip. All right. We're doing an APQ already.
Alright.
Yep, we're ready. Well, ready as we'll ever be. If f of x equals ln of x over x for all x greater than 0, which of the following, this is just something that they need to say in order to be mathematically precise. Like if a function, if the AP is using a function that has a restricted domain, like ln or square root, they just have to say its domain. You don't really need to like worry about that though. You're like, cool, I'm ignoring it though. You know, like it's not, it's not gonna, don't focus on that. Okay, which of the following is true? Increasing for all x greater than 0, increasing for all x greater than 1, decreasing for x between 0 and 1, decreasing for x between 1 and e, decreasing for x greater than e. Okay.
I don't think it's any difference.
Why is that?
Because it's always positive.
So ln increases. Where does ln increase? Always. Okay? Always. Great. Where does x increase? Like if I was just graphing x, y equals x. Always. Make sense? What if you take, like, write this line? What if I take something that increases and divide it by something that increases? Do you think that thing will still increase, or that'll like make it decrease?
Divided by something that decreases.
No, I have something that increases divided by something that's increases.
It'll keep increasing.
It'll keep increasing, yeah. Right? So this function increases always over its whole domain. Go ahead and pick that answer. Okay. Alrighty, let's keep going over log rules, alright? So here I have this little chart of just some tables of values that we went over on the graph, but it says like ln of 1 is 0, ln of infinity is infinity, ln of e is 1, right? Okay, we got some stuff. Alright, what's ln of 1? 0. Boom. What's ln of e? 1. Great. So we have a product rule in calculus, right? This is the logarithmic product rule. Totally different. They just both involve products.
ln of a plus ln.
Yes.
Look at
Wait,
you,
what?
Jackie.
Okay.
Oh my god.
So
This is the only thing I remember from last year. Look at this last year. We learned all the rules.
Wait, it's like way there.
okay.
First period on Zoom.
Okay.
I remember reading the page.
Okay, so if you have, so this thing that you take the log of is called an argument. So just like with trig functions, it's a lot like trig functions in that, so if you have 2x, right, you can separate the 2 and the x, like they can be separated, obviously, right? Like 2. If you have sine of x, you can't separate them. This is the argument, no. This is the, what's called the argument, it's like what, you have to take the sine of something. It's never sine with nothing here. You have to take the sine of something, an angle. Like you can't, this is not a thing. Okay, you have to have an argument. Log is the same way. Log, and by the way, when I say log, natural log is a log. So when I say log, I can mean like log base 10, log base 2, natural log. Just, if I don't say ln, but I say log, ln is a type of log. Got it?
Wait, repeat that?
So, so some people always refer to ln as ln, or natural log. But some people just, it is part of, it is a logarithm, ln is a log. So if I say log, you're thinking in your mind, natural log.
Is
Okay?
there a unnatural one?
Everything that's non-ln, all the other logs. Like on the do now, we did log base 3. That would be an unnatural log, log base
Why?
3.
LN is natural.
Wait,
Right.
but why is it N, why is it not NL?
Natural log. Because you want to start with the log is the more important
Wait,
word.
this is actually a genuine question. So you said we did log base 3,
Yes,
right?
on the
How
do
is
now.
that one's not natural log again?
Because the base isn't e. So, okay, let's do this. ln
This is a secret
of
thing,
x
right?
has
It's just
A
not
base
this, it means it's a little-
of e. Okay? So what does that mean? What, like when I say that, what does that mean? It means that
It has a subscript.
the inverse of y equals ln of x is y equals e to the x. So those are inverses. Remember how like on the do now, we did it 3 to the x was the inverse of log base 3 of x, and all the points were switched. So if I wanted to graph points, and I knew the points of this one, I would just switch all the x's and y's and graph that one. So when I say it's base e, it means that's the inverse of e to the x. By the way, this is called a base, right? This is the base, that's the exponent. So the word is the same, base e, and its inverse is base e.
It's gonna take a while to do in my head.
Yeah, it's gotta simmer, it's gotta simmer. So if you have log of a product, that is the sum of 2 logs. So see how there's like ln written once and then it ends up being written twice?
Yes.
So like common mistake would be like ln of like a plus b, like that's wrong.
That's probably how I would.
Yeah,
But when
So-
you look at it, that's
yeah. So log of a product is the sum of 2 logs. One product
of a product
is the sum of 2 logs. Okay? Yeah, let's write it down. Log of a product logs. And this is why I went into the whole diatribe on like when I say logs, like in this sentence, ln is included in that.
Unless otherwise formally.
Okay. Let's skip and let's do this one. Log of a quotient.
No, let's not skip, let's go through everything.
We only have.
No, we're gonna go back to this. Oh yeah, I'm just gonna do it in a different order. Yeah. Log of a quotient. What do you think log of a quotient is?
Is
The difference of two logs. Log of a quotient is the difference of two logs. Okay, so let's do this one. Yes. So ln of a minus ln of b. That's how this one would be. Oh, let's put the a and the b in parentheses for now. Okay. Now this one is called the power rule, actually. So it's not like the calc power rule, but so you know when you raise a power to a power, you multiply. So this is a power, so you end up multiplying. So I like this one. I don't have a little chant for. I have a visual. You put it out in front, and that exponent becomes a coefficient. This equals n ln of a. So exponents become coefficients for
I
logs.
remember that.
Oh, I remember this one too.
I don't know what, I don't remember this.
I remember this from last. Logan, you were
This
so
must have happened to
useless,
you.
right?
No, because my.
Logan, I would always private chat you and you would never be helpful.
Because it's you don't understand.
Okay, we're about to end. Can you talk to your neighbor about what you learned today about logs? You should have a lot to say.
Literally everything.
I learned that log of probably the base of probably.
Like, what is ln maybe? What's our definition of ln?
Natural laws.
No, that's what